Hi students, welcome back to second session of coordination chemistry. In the previous class, we had discussed about what are double source, what are coordination compounds, what are the difference between double source and coordination compounds, and IUPAC nomenclatures. What are the certain rules? We have studied rules to assign IUPAC nomenclature for a coordination compounds. Okay, I hope everything is clear. Now let's move on to the next topic. Awareness theory. So awareness theory of coordination compounds. Okay. So in 1893, Alfred Werner proposed this theory in order to explain nature of metal complexes and concept of valency, and he was also awarded a Nobel Prize for his contribution towards coordination compounds in 1930, and he was also known as father of coordination chemistry, and he was given few postulates. Let's see one by one. Postulates of Werner's theory. Okay, so the first postulate was, so every metal atom exhibit two types of valences. Every metal atom exhibit two types of valences. What are they? Primary valency and secondary valency. Okay, so primary valency, secondary valency. So primary valency is also known as ionizable valency. Ionizable valency, and which is corresponding to oxidation state of center metal atom. Oxidation state of center metal atom, and so most probably primary valence is satisfied by negative ions. And in the structure, this primary valence is represented by dotted lines. In the structure, so dotted lines in the structure, and satisfied by negative ions. Okay, these are the few points regarding primary valence. Okay, I will repeat it again. Primary valency is also known as ionizable valency, and it is corresponding to oxidation state of center metal. For example, if you want to know primary valency, if you given one complex, so what is the primary valency of that complex? That is, you simply calculate oxidation state of center metal atom. So that will be equal to your primary valency, and this primary valency is satisfied by negative ions, and in the structure, this primary valency is represented by dotted lines. Okay, coming to secondary valency. Okay, secondary valency is non-ionizable valency. Secondary valency is also known as non-ionizable valency, and which is corresponding to coordination number, and most probably negative ions and neutral molecules satisfying this secondary valency. And in the structure, this secondary valency is represented by thick line. Okay, so there are a few points regarding secondary valency. Okay, the first postulate is, so every metal atom in the complex, in complex containing metal atom and ligand. So that metal atom will exhibit two types of valencies. One is primary valency, and second one is secondary valency. Okay, so primary valency is also known as ionizable valency, and it is corresponding to oxidation state of center metal atom, and it is satisfied by negative ions, and it is represented as dotted lines in the structure. Okay, next, secondary valency. Secondary valency is also known as non-ionizable valency, and it is corresponding to coordination number. If you want to know secondary valency of a complex, if you want to know secondary valency of complex, you just see the coordination, how much coordination number it is having. So that will be equal to secondary valency. Okay. Now it is most probably the secondary valency is satisfied by negative ions and neutral molecules. In the structure, the secondary valency is represented by thick lines, solid line. Okay, this is first postulate. And the second postulate, so every metal atom has tendency to satisfy both primary valence and secondary valence. metal atom has tendency to satisfy primary valency and secondary valency. For this purpose, so most often negative ions exhibit dual behavior. So dual behavior means sometimes the negative ions, most probably the negative ions satisfy both primary valency, secondary valency. May often satisfy both primary valency and secondary valency. That is dual behavior. Okay. What are those? Negative ions. Okay. Negative ions satisfy both primary valency and secondary valency in some cases. That is postulate number 2 and postulate number 3. Dual behavior, and every metal atom has a fixed number of secondary valencies. So every metal atom has a fixed number of secondary valencies. So what I have told you, secondary valency is corresponding to coordination number. Okay, so coordination number is fixed. Okay, if you have 4 ligands, that coordination number is 4, and the secondary valency is 4. Okay, that is 6. 4 is fixed. If you have 6 ligands, 6 ligands are surrounded by the metal atom with its coordination bond. Now that's coordination number 6 is fixed. Okay, that coordination number is corresponding to secondary valency. That means every metal atom has a fixed number of secondary valencies. That is postulate number 3 and postulate number 4. So the secondary valencies are oriented. Okay, directed towards some fixed positions. Fixed positions in the space. Okay, so this is postulate number 4. So what is this one? What is this means? The secondary valency are towards oriented towards central metal atom in fixed positions around the central metal atom in a fixed position. If you are having, for example, if you are having 4 coordinate complex, 4 coordinate complex means around the central metal atom they are having 4 ligands. So these 4 ligands are either in a tetrahedral manner or in square manner. So I have a model, I will show you. So this is 4 coordinated complex. Okay, so this is 4 coordinate complex. So 1, 2, 3, 4, and black ball is your metal atom, and white balls are represented as ligands. Okay, represents the ligands. Now the 4 ligands. So this is the coordination. The coordination number of this central metal is 4 because we are having 4 ligands, which is correspond to 4 ligands. So these secondary valencies are around the central metal have fixed positions in a tetrahedral corners. So the structure is tetrahedral. Having bond angle 109 degrees 28 minutes, 109 degrees 28 minutes, 109 degrees 28 minutes, 109 degrees 20 minutes. Okay, or so square panel. Okay, the 4 ligands around the central metal atom either in a tetrahedral manner or in square planar manner. So that depends upon hybridization. I will talk about in the next topic about hybridization. Okay, let's see the 4 ligands are arranged in a square planar manner in the structure. Okay, so this is the coordination number is 4, the second valence is 4. So these 4 ligands are in fixed positions. That is square planar manner. Okay, so one angle is 90 degrees, 90 degrees, 90 degrees, 90 degrees. In tetrahedral, 109 degrees 28 minutes. Okay, if you are having 6 ligands around the central atom, so the structure is octahedral. Octa means 8, hedral means faces. That means the structure having 8 trigonal faces. 8 trigonal faces. If you see that this is the structure of octahedral. Okay, so here having 6 ligands. 1, 2, 3, 4, 5, 6. Okay, 6 ligands. So along x-axis we are having 2 ligands. Along y-axis we are having 2 ligands. Along z-axis we are having 2 ligands. Total 6 ligands. Okay, so total 6 ligands. These 6 ligands are in octahedral corners. Okay, along x-axis, y-axis, and z-axis. So these 6 ligands are fixed around the central atom. Okay, so this is about 4 points. So these are the postulates of valence theory. Okay, just a few reasons. Let's see. The first postulate was every metal atom has exhibit 2 types of valency: primary valency and secondary valency. Primary valency is corresponding to oxygen state, and it is also known as ionizable valency, and it is that's why the negative ions and the structure is denoted by dotted lines. And the secondary valency. Okay, secondary valency is non-ionizable valency, and it is this correspond to coordination number, and most probably the secondary valence has been negative ions and neutral molecules in the structure. This can be represented as a thick line, dot line. Okay. And the second point, most probably negative ions exhibit dual behavior. Negative ions in some cases, some situations, most often negative ions are having dual behavior. That means most of they may satisfy both primary valency and secondary valency in some cases. Okay. And the third point is every metal atom has a fixed number of secondary valencies, because a secondary valence is coordination number none. So they have coordination number is fixed, either 4, 5, 6 or 3. So what number of ligands we are having, that depends upon. Okay. Next, these secondary valences are around the center metal in fixed positions, directed towards some fixed positions around the center metal. If you are having 4 coordinate complex, the 4 ligands are arranged in a tetrahedral manner or square manner manner. If you are having 6 ligands, these 6 ligands are arranged in a octahedral corners. Okay. And so these are the postulates of Werner's theory. And Werner's most extensively studied chloroimine cobalt-3 complexes. Chloroimine cobalt-3 complexes. He was taking 4 complexes and explained their nature and structures. Okay. The first complex is COCl3 6NH3. The complex. Okay. Next COCl3 5NH3. COCl3 4NH3. COCl3 3NH3. Okay. The complex form, this can be formulated as complex ion form NH3, this can be written as CONH3 6 times Cl, and this is CONH3 5 times Cl, CONH3 4 times Cl2, 4 times and Cl, and CONH3 thrice Cl3, right? We are having 4 complexes here. Now, here this part will ionize. Previous class I told you, no? So this part will ionize, and this part will not ionize. Will not get ionized. Okay, because this is coordination sphere, na? Okay. This part will not ionize. This part will ionize. So in aqueous solution, so number of ions. This when this complex dissolves in aqueous solution, how many number of ions is given by this complex? Just ionize it. Right? This can be ionized as CONH3 6 times and 3 Cl. So this is ionized here. So this 3 chlorine has 3 Cl minus. So this can be ionized as CONH3 6 times by balancing 3 plus, because of here having 3 chloride ions. So CONH6 and 3 plus and 3 Cl minus. Total 1. So these are 1 cation, 1 plus and 3. Total 4. So number of complex. So number of ions in solution. Number of ions in solution. So number of ions in solution. So this is complex cation. CONH6 and 3 plus. 1 complex cation and 3 anions. That is 3 Cl minus. 1 plus 3. So total 4 ions in the aqueous solution. So you are getting 4 ions in aqueous solution when it is dissolved in the solution, right? Now coming to this complex. Now this complex dissolved in aqueous solution. How many ions you are getting? So just ionize them. So this part will ionize. This part will not get ionized. So this part is 1. So CONH6 times. Here 2 chlorides. Each chloride having negative charge over the chlorine atom. So you have 2 Cl minus. This can be balanced by the charge over the coordination sphere. So this can be ionized as CONH3 5 times. Here 2 plus and 2 Cl minus. Overall, how many ions? These are 1 ion plus, and this 2 anions. 1 cation and 2 anions. 1 plus 2, 3. So 3 ions in an aqueous solution. Okay. Now coming to third complex. So this can be ionized as CONH3 4 times Cl2 plus Cl minus. Okay. We are having only 1 chloride in ionization sphere. So this cation, 1 cation and 1 anion. So 2 ions. Now last one. So how many ions here? Here CONH6 and NH3 thrice Cl3. So is it 1? No. Because why? Because here this is not ion. You are not having any charge over the coordination sphere. So this is neutral molecule. This is not ion. This is a neutral molecule. So this is not ion. So no ions in aqueous solution. So 0 ions. Okay. And next. Now, so this complex solution, we are having complex, the solution of this complex. Now, treating with the AgNO, the solution. So we are having chloride. So 3 Cl minus. Now, basically what are doing in laboratories for test for chloride, confirmation test for chloride. So having the, for example, we are having solution. Now test for chloride. So what you are adding? AgNO, silver nitrate. So silver nitrate which contains Ag plus and NO3 minus. Ag plus will react with the Cl minus and forming AgCl precipitate. Okay, AgCl precipitate. So in the same way, now we are having this complex. Now this complex is the aqueous solution which gives CuN6 plus and 3Cl minus. We are having 3 chloride ions in free state. So 3 ions in the ion form. So these 3Cl minus are reacted if we are adding AgNO solution. AgNO3 solution to this complex solution. Now this 3Cl minus are reacting with Ag plus ions because we are having 3Cl minus ions here. Okay, in this aqueous solution. Now these 3Cl minus ions are reacting with Ag plus and forming AgCl by precipitate. Okay, that means number of Cl minus ions precipitated as AgCl. So how many chloride ions are available to react with Ag plus? That means now we are adding AgNO3 solution to this complex solution. AgNO3 which contains Ag plus and NO3 minus. Ag plus reacting with these 3 chloride ions are forming 3 AgCl white precipitate. That means number of chloride ions are reacting with Ag plus ions. How many number of chloride ions are reacting with Ag plus solution? That is Ag plus ions. That is 3. So 3 chloride ions because we are having 3 chloride ions. Okay. Now coming to second one. Okay. So this complex will dissociate as CONC 5 times Cl 2 plus and 2 Cl minus. Total number of ions are 3. 1 plus 2 3. Okay. Now adding AgNO3 solution containing Ag plus ions solution. Now AgNO3 solution adding to this complex solution. Now how many chloride ions are reacting with Ag plus ions and forming AgCl precipitate? Okay. So by simply looking over this complex, here also we are having 3 chloride ions now, but 1 chloride ion present in coordination sphere. So what I have told in previous class, so within the coordination sphere, the ions are not available in free state. That is not ionized. So this part will ionize, but this part will not ionize. Will not get ionized. So this Cl is not available as Cl minus. So the Ag plus ions are reacting with the chloride ions only if they are in the form of ion form. But these chloride ions are not dissociated as Cl minus. So that's why this chloride ion not reacting with the Ag plus solution, the Ag plus ions in the solution. But out of this coordination sphere, that is in ionization sphere, we are having 2 chloride ions. But these 2 chloride ions are available as 2Cl minus. 2Cl minus. Only these 2 chloride ions, because these 2 chloride ions having in the form of minus, that is anionic form. So these 2 Cl minus ions are reacting with Ag plus ions and form AgCl precipitates. Now how many chloride ions are reacting with Ag plus ions and forming AgCl precipitate? 2. Even though you are having 3 chloride ions, but 1 chloride ion is within the coordination sphere, that chloride ion will not get ionized because it is present in the coordination sphere. That's why this chloride ion not reacting with Ag plus ions and not forming AgCl precipitate. But the 2 chloride ions which are present outside this coordination sphere are reacting with the Ag plus and forming AgCl white precipitate. Okay. Now coming to third complex, CONC 4 times Cl to Cl. So this can be ionized. We are giving in the solution we are having 2 ions. 2 ions, that is this can be dissociated as ionized as CONC 4 times Cl2 2 plus and Cl minus. Okay. So 2 ions. Now here also having 3 chloride ions. So all these complexes are having 3 chloride ions. All these complexes are having 3 chloride ions. But in the first complex, the 3 chloride ions are present in outer sphere, that is ionization sphere. In the second complex, only 2 chloride ions are present in outer sphere. And the third complex, only 1 chloride ion is present in outer. The Ag plus ions are reacting with the Cl minus ions. Here 3 chloride ions are available. Here 2 Cl minus ions are available. Here 1 chloride ion is available. That means how many chloride ions are reacting with Ag plus ions here in this complex? Only 1. These 2 chloride ions are not reacting with Ag plus because these 2 chloride ions in coordination sphere, which is not ionized. Okay, so how many chloride ions? 1. Next, coming to this. See here, all these 3 chloride ions in coordination sphere. So these so no available of Cl minus ions to reacting with the Ag plus ions in the aqueous solution. So you are having no. So no chloride ions are precipitating as that is these 3 complex will give white precipitate, but the fourth one will not give any white precipitate because it does not react with the Ag plus. Because here 3 chloride ions in coordination sphere, so not reacting with the Ag plus ions because these 3 chloride ions are not in free state, not in ionic state because they are present in coordination sphere. Okay. Next, molar conductivity. So one more property is given by Werner. So that is molar conductivity. So first, what is conductivity? So conductivity nothing but flow of ions. If in solution, number of ions increases, conductivity increases. Number of ions increases, conductivity decreases. Okay. So first complex. So if you compare the molar conductivity of all these four complexes, which one having more molar conductivity? Absolutely first one. That means because here having 4 ions in aqueous solution. So here 4 ions, 3 ions, 2 ions and no ions. So what I told you? So conductivity is nothing but flow of ions. If number of ions increases, conductivity will increases. So here 4 ions, 3 ions, 2 ions and 0. So molar conductivity for this complex having more value. Okay, so around approximately 4 inverse. So around 404 and this is around 229. This is around 97. So this is no molar conductivity because we are not having any ions. Okay, that's why 0. Okay, right. So next, so this is all about complexes which are studied by Werner, right? Next, the structure of this complex. For example, first postulate. What is first postulate? Every metal atom exhibit 2 types of valency: primary valency and secondary valency. So for example, taking this complex. Okay, what is the primary valency of this complex? So primary valency is ionizable valency. So this part will ionize. So this can be ionized as C1 and 3 plus and 3 Cl minus. So overall 4 ions. The primary valency which is corresponding to oxidation state. So oxidation state of central metal atom. How to calculate oxidation state of central metal atom here? So in the previous class I told you that. So cobalt oxidation state can be calculated as. So let us say X. Oxidation state of central. You don't know the oxidation state of central metal atom. So let us say X plus 6 into. So ammonia. So ammonia is neutral molecule. You don't have any charge over the molecule. So 0, no charge. That means 6 into 0 equal to the overall charge over this coordination sphere. So this can be ionized as C1 3 plus and 3 Cl minus. So over the coordination sphere, they are having 3 plus, 3 positive charge. That means so this can be equal to 3 plus 3. Okay. So X comes out to be 3. So oxidation state of cobalt here 3. So which is corresponding to that means primary valence of cobalt here 3. So 3 Cl minus are available. So these 3 Cl minus are satisfying primary valency. And what is secondary valency? Secondary valency is non-ionizable. So these cobalt and ammonia are non-ionizable. So this secondary valency is corresponding to coordination number. Here what is the coordination number of this complex? 6. Coordination number is 6. 6 ligands are around the central atom. Coordination number is 6. That means for this complex, the primary valency is 3 and the secondary valency is 6. Primary valency is 3 and secondary valency is 6. Okay. Next, coming to this complex. What is the primary valency of this complex? So primary valency. So by simply looking over this complex, the primary valency. So primary valency is 2, but the primary valency is 3. So what is the second postulate? Most often, in some cases, the negative ions are satisfying both primary valencies and secondary valency. Okay. See a chloride ion. So this chloride ion exhibit dual behavior. That means this chloride ion satisfying both primary valency and secondary valency. So because if you calculate the oxidation state of cobalt here, so cobalt oxidation state. So cobalt oxidation state, let us say X. Okay, X plus ammonia is neutral ligand 5 into 0 plus Cl minus. When you write Cl, so here you put negative charge over the chloride ions. That means Cl as Cl minus. That means negative charge. But one chloride ion is available 1 into minus 1. So that equal to. So overall charge on the complex. So if this complex ionized as C1 is 5 Cl 2 plus and 2 Cl minus. So over the coordinate sphere we are having 2 plus. Okay, 2 positive charge. This plus 2. Okay, the X comes out to be 2 plus 1 that equal to 3. So here also the coordination number is the primary valency is 3. The oxidation state is 3. Here also 3 and here also 3. So this, if you calculate the oxidation state of this cobalt ion, also comes out to be plus 3. And here also plus 3. So in all this complex the primary valency is common, that is 3. But here the 3 chloride ions are satisfying primary valency and 6 ammonia are satisfying secondary valency. Now here also coordination number is 6. 5 plus 1 6. 4 plus 2 6. 3 plus 3 6. So all these complexes are having 6 coordinations. 6 secondary valency, 3 primary valency. But second complex, if you see the second complex, this chloride ions satisfying both primary valency and secondary valency. So primary valency 1 plus 2 3. Okay, 3. Primary valency is 3. And secondary valency 5 plus 1, 6. That means this chloride ion satisfying both primary valency and secondary valency. That means this chloride ion is exhibiting dual behavior. Okay, now coming to this complex. So here 4 plus 2, coordination number is 6. That is secondary valency is 6. And this primary valency is also 3 because cobalt X plus 4 into 0 plus 2 into minus 1. So if you can analyze this complex, Cl is 4 times Cl2 plus and Cl minus. Cl minus this can be balanced by positive charge over the complex plus 1. Okay, so equal to plus 1. So X comes out to be 2 plus 1, that equal to 3. Here also the oxidation state is 3. That means primary valency is 3. That means these two chloride ions are satisfying both primary valency and secondary valency. Now coming to last complex, this complex C1 is thrice and Cl3. Okay, now this complex can be here neutral. This complex is neutral molecule. Neutral molecule. If you calculate the oxidation state of this complex, cobalt in this complex. So X oxidation state of cobalt plus 3 into 0 plus 3 into minus 1 overall charge of the complex. Overall charge of the complex is 0. So that is equal to 0. So X comes out to be plus 3. X equal to plus 3. Okay. Here also oxidation state is plus 3. That means primary valency is 3. That means these three chloride ions. So these three chloride ions are satisfying both primary valency and secondary valency. Primary valency is 3 and secondary valency is 6. Okay. Now if you see the structures of these complexes, the first complex C1 is 6 times. So coordination number 6. The structure is octahedral. Okay. CO NH3 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 NH3. So this is structure of octahedral. All these ammonia acts as ligand. So these ammonia are representing dual pair of electrons to this environment atom and forming coordinate bond. Okay. Now, so all these ammonia molecules are satisfying secondary valencies. And these three chloride ions satisfying primary valencies. I told you now the first point of primary valency are represented as dotted lines and secondary valency represented as thick lines. Okay. So chloride and chloride. Okay. So but when you write the structure of complexes, just ignore this 3Cl minus actually. But actual representation is this secondary primary valency represented dotted lines and the secondary valency represented thick line. Now coming to second complex. So this chloride is satisfying both primary valency and secondary. So how can you represent this in structure? CO chloride NH3 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 NH3. Okay. So now this chloride ion satisfying both primary valency. So what I told you. So this chloride ion satisfying both primary valency and secondary valency. So primary secondary valency thick line and this is dot lines. That means this structure is represent this chloride ion satisfying secondary valency and primary valency both. Okay. So and then so these two chloride ions are in outer sphere, that is ionization sphere, available as Cl minus. But this chloride ion is not available as Cl minus. That's why it is not reacting with Ag plus and not forming AgCl precipitate. Okay. So similarly this complex two chlorides are satisfying primary valency, two chlorides are satisfying primary valency and secondary valency also. If you write the structure of this complex, CO coordination number is 6, Cl NH3 Okay. So these two chloride ions are satisfying both primary valency and secondary valency, And the third one, this can be represented as dot lines. So only this chloride ions are available as in the ion form, that is Cl minus ion form. Okay. So these two chlorides are satisfying both primary valency and secondary valency. Okay. NH3 4 times. Now coming to the fourth complex, last complex, C1 is the thrice Cl3. CO NH3 Cl. C1 is the thrice Cl3. So these three chlorides are satisfying both primary valency and secondary valency. Okay, I hope you got it. This point. Next, what are the defects? Defects of coordination. So defects of Werner's theory. So for first defect, here we are having a few defects. The first defect is, so Werner's explained main structures from many complexes, but it does not explaining what is the nature of bonding between the metal and ligand. That is first defect. It doesn't explaining nature of bond between metal and ligand. And next, cause of various properties. It doesn't explaining. Werner's theory doesn't explain cause of various properties like color, binding properties, spectra. Okay, all those things which are not explained in this theory. And second one, and this theory fails to explain why certain four coordinate complexes are formed tetrahedral. In previous and a few minutes ago, I will show you four coordinate complex now. Which one is forming tetrahedral and the one forming square planar. So that means this theory fails to explain some four coordinate complexes are forming tetrahedral, some four coordinate complexes are forming square planar complexes. So these are the defects of this theory. Okay, I hope everything is clear. Okay, let's move on to the next topic. Sidgwick's concept of coordination. So Sidgwick's concept of coordination compounds. Okay, so Sidgwick's in 1923. So Sidgwick's in this theory used Lewis concept. Lewis concept. So what is Lewis concept? You previous maybe level the 12th standard. You know Lewis acid, Lewis base. Okay. So the species which are accepting electron pairs are called Lewis acids. Accepting electron pairs. That means electron pair acceptors. Electron pair acceptors. Lewis bases. Electron pair donors. So electron pair donors. So okay, the species which are capable to accepting electron pairs are called Lewis acids. The species which are available of lone pair of electrons for donation are called Lewis bases. Okay, so that is Lewis concept. Now in metal complexes, so which one acts as a Lewis acid, which one acts as a Lewis base? You know, in metal complexes we are having metal and ligand. So for example, if you quotation number 6, this is a complex. Now here, what is the necessary condition here? So metal makes available of vacant orbital for accepting electron pairs from the ligand, and ligand having lone pair of electrons. So ligands having lone pair must have lone pair of electrons for donation, and metal having vacant orbital for acceptance. Okay, electrons. So those electrons donated by ligand. That means here metal is acceptor. Metal is acceptor. So metal is acceptor. So acceptor is Lewis acid. Metal is acts as Lewis acid, and ligand acts as Lewis bases because ligands are donor. Okay, ligand is donor, metal is acceptor. Okay, right. So the bond is represented as an aroma from ligand to metal. So this bond is called coordinate bond or day-to bond. Coordinate bond or day-to bond or semi-polar bond. Okay, this bond is called coordinate bond or day-to bond or semi-polar bond. Okay, that is the structure. For example, you see the structure of CONH3 6 times 3 plus. So this structure can be written as H3. So ammonia having lone pair of electrons on the nitrogen. So donating its lone pair of electrons to the metal and forming coordinate bond. Okay, so this is donor and this is acceptor. Okay, in that way, so this ammonia donating one lone pair of electron, this ammonia donating one lone pair of electron, and this ammonia donating one lone pair of electron, and this ammonia NH3, NH2. Total 6 ammonia molecules, each ammonia having one lone pair of electron. Then donating this lone pair of electrons to total 6 lone pair of electrons from 6 ligands. Okay, donating to this central metal atom cobalt. Okay, so this is all these regarding Sidgwick's. Okay, first thing is Sidgwick's in his theory used Lewis concept. What is Lewis concept? So according to Lewis, Lewis acids are the species which are accepting electron pairs. The electron pair acceptors are Lewis acids. Electron pair donors are called Lewis bases. That means these are acceptors and these are donors. Now here metal complexes, so metal is acceptor. Here necessary condition, metal is accepting electron pairs and ligand donating electron pairs. Okay. Now metal is acceptor, ligand is donor. So the bond is represented arrow mark from ligand to, from donor to acceptor. Okay. And Sidgwick also suggests one rule that is called effective atomic number. Effective atomic number. Sidgwick's effective atomic rule. Effective atomic number, that is EAN rule. EAN rule. Sidgwick's EAN rule. He suggests effective atomic number rule. That's EAN. So what is this rule? Okay, according to what is the definition of EAN? So the total number of electrons present on the metal, total number of electrons present on metal, total number of electrons present on metal plus number of electrons donated by ligand. Okay, so that is effective atomic number. So what is effective atomic number? The total number of electrons donated by the ligand and number of electrons donated by the ligand. So this sum, which is EAN, effective atomic number, which is equal to nearest inert gas configuration. Nearest inert gas configuration, that is for example krypton 36, xenon 54, radon 86. If atomic number equal to, so this sum which is equal to 36, that is corresponding to atomic number of krypton, that is inert gas, that is more stable. Okay, and xenon 54 and radon 86. This is equal to nearest inert gas atomic number, so that complex is more stable. Okay, let's understand with the help of examples. So first I am taking FeCN6 4 minus. FeCN6 4 minus. First, what is the name of this complex? This is anionic complex. Over the coordinates here we are having negative charge. That means this is a anionic complex. The coordination number is 6. That means hexacyano. Over the coordinates we are having negative charge. That means the metal ending with 8. That means hexacyanoferrate. The oxygen state here 2. Oxygen state of iron is 2. What can you calculate here? How would you calculate? So you don't have oxygen state of centimeter atom, that is iron here. Let us assume X plus 6 into over the cyanide we are having negative charge. One negative charge now. That means 6 into minus 1 equal to the charge over the coordination sphere, that is minus 4. So X equal to plus 6 minus 4. X comes out to be plus 2. Oxygen state of iron here 2. Oxygen state of iron here 2. Okay, now what is EAN? Total number of electrons present on the metal. So total number of electrons present. So total number of electrons in iron. So for that we have to know at least 3D series elements. 3D series elements, their atomic numbers and electron configuration you must know. Okay, for example, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. From 21 to 22, 23, 24, 25, 26, 27, 28, 29 and 30. Okay, scandium 21. So total number of elements in scandium 21. 3D series elements. So all these are 3D series elements from 21 to 30. And then electron configurations. So argon 3D1 4s2. 3D1 4s2. Here titanium, argon 3D2 4s2, 3D3 4s2, 3D4 4s2, 3D5 4s2, 3D6 4s2, 3D7 4s2. These are the valence electrons. Okay, total number. So total number of electrons are 24. For example, take chromium. Total number of electrons are 24. Valence electrons are 4 plus 2 6. Okay. Now nickel. 3D8 4s2, 3D9 4s2 and 3D10 4s2. See, a chromium and copper abnormal configuration. configurations we know that. So for off-fill and full-fill configurations are most stable. For that, the electron jumps from 4s to 3d because there is less difference between 3d and 4s. So easily the electron from 4s easily jumps electron from 4s to 3d. That means this configuration becomes 3d5 4s1, 3d5 4s1, and here also completely electron configurations are so stable. So that's why electrons are jumping from 4s to 3d. That means that the configuration of copper becomes 3d10 4s1, 3d10 4s1. These two are abnormal configurations, so you have to keep in mind. Okay, now iron. So total number of electrons present on the metal. So total number of electrons present on the metal. Iron is 26. 26. So total number of electrons present on metal, that is 26. 26 electrons, total electrons. And the oxygen state is +2. So +2 means iron in this complex iron in its +2 oxygen state. +2 means losing 2 electrons. So plus means losing, minus means gaining. Okay, so +2 means iron is losing 2 electrons. That means total number of electrons are present on metal. Iron is 26. Iron 2 positive, Fe 2 positive is 26. 2 plus means losing 2 electrons. That means 26 minus 2, 24. Okay, next 6 cyanide ligands. 6 cyanide ligands. Each cyanide is monodendron ligand. Cyanide is at a time donating 1 lone pair of electrons to this central metal atom, that's iron. So each cyanide donating 1 lone pair of electrons. We are having 6 cyanide atoms. So cyanide molecules. Now 6 into 2. Plus number of electrons donated by the ligand. That means 6 into 2, that is 12. So that is 36. That is krypton configuration. So this complex is stable. Okay. That means I repeat it again. So FeCN6 4 minus. First we have to calculate the oxygen state of central metal atom. We have to calculate the oxygen state of central atom, that comes out to be +2. Okay. Now first, what is the definition of EN? Total number of electrons present on the metal plus number of electrons donated by the ligand. Number of electrons donated by the ligand. Now iron is having 26 electrons. 26 electrons. Fe2 plus iron having 26 electrons. Fe2 positive. That means Fe losing 2 electrons. Now here 3d6 4s2. Now 2 electrons are losing from 3d or 4s. So here it is 4s outermost shell. So electrons are losing from 4s orbital first. So the 2 electrons are removed from 4s. That means this configuration becomes 3d6 4s0 in Fe +2 oxygen state. That means total number of electrons are 26 minus 2, that is 24. So total number of electrons present on metal is 24 plus number of electrons donated by the ligand. So each cyanide donating 2 lone pair, that is 2 electrons, that is 1 lone pair. 1 lone pair means 2 electrons. Okay, 1 lone pair means 2 electrons. So 2 electrons. Now total 6 cyanides, 6 into 12 electrons. So they are 24 plus 12, that is 36, which is equal to nearest and nearest configuration, that is krypton 36. Okay. Now let's take another example. CONH3 6 times 3 plus. CONH3 6 times 3 plus. Cobalt. So what is the unit nomenclature for this complex? Hexaimine. So all the coordinations here are having positive charge. That means the metal name as it is. That is hexaimine. Cobalt. Oxygen state of cobalt here. Ammonia is neutral. Ammonia is neutral molecule. So that means X plus 6 into 0, which is equal to the charge over the coordination sphere. That means X plus 6 into 0 equal to +3. Okay. So here oxygen state of cobalt here +3. So 3 positive. Okay. So total number of electrons present on the metal is cobalt. Cobalt is 27. Total 27 electrons are present in cobalt. So cobalt 3 plus, that means losing 3 electrons. So 27 minus 3, that is 24 electrons. Okay, cobalt having 27. So cobalt 3 plus means 24 electrons, losing 3 electrons. So losing 3 electrons first, the 2 electrons are losing from 4s. That means one more electron removed from 3d. That means the configuration becomes 3d6 4s0 in cobalt +3 oxidation state. Cobalt in free state, in neutral state, that means cobalt 3d7 4s2. Cobalt in ionic state, for example, here I have cobalt +3 oxidation state. +3 means losing 3 electrons. So losing 3 electrons. That means 27 minus 3, that is 24, plus number of electrons donated by the ligand. So here 6 ammonia molecules. 6 ammonia. So ammonia also having 1 lone pair of electron. It is a monodentate ligand. Monodentate ligand. That means 1 lone pair of electron donating 1 lone pair of electrons to the center metal atom. That means 6 ammonia. Each ammonia having 2 electrons. That is 1 lone pair, 2 electron. Now 6 ammonia molecules donating 6 lone pair of electrons to the metal atom. That means 6 into 2. equal to 12. That is also comes out to be 36. That is equal to krypton configuration. So this complex is also stable. Okay. And let's take another example. NiCO4 tetracarbonyl nickel 0. So this is neutral complex. Just try this complex, friends. Just pause the video and just try this. What affected atomic number for this complex? Okay, nickel. Here nickel oxygen state. Nickel oxygen state here 0. So carbonyl is 0. Carbonyl is neutral molecule, that means no charge. So X plus whole into 0 and overall charge also 0. No charge here. That means nickel oxygen state is 0. Means we are having nickel 28 electrons. Nickel having 28 electrons. Nickel 28 electrons and 4 carbonyl. Carbonyl also monodental ligand. So carbon having one pair of electron, oxygen having one pair of electron. But at a time, donating one pair of electron, either carbon or oxygen. Most probably carbon is one pair of electron because carbon having less electronegativity. So because of less electronegativity, carbon most probably donates one pair of electrons rather than oxygen. Okay. So 4 carbon is 4 into 2, that is 8. So 28 plus 8. 36. This complex is also stable. Okay, right. So in that way, you can try a few more examples. Last slide, explain one example. It is not obeying AKNU. FeCN6 3 minus. Let's take another example. FeCN6 3 minus. Okay, so here iron oxygen state is just calculate x plus 6 into minus 5 is minus 1. 6 into minus 1 equal to minus 3. X equal to 6 plus 3. Sorry, 6 minus 3 comes out to be plus 3. Iron oxygen state is plus 3. So iron Fe 26 electrons. We are having 26 electrons. Fe plus 3. Fe3 plus Fe3 positive having 26 minus 3. That is 23 electrons. Okay, so total number of electrons present on metal is 23 or 23. Okay. Next up, 6 cyanides, 6 here minus 6 into 2, that is 12. So 35 is not equal to 36. So this complex is unstable. So FeCN6 3 minus and the first example FeCN6 4 minus. So if you take these two complexes, which one is stable? FeCN6 4 minus. Ferro, this is ferrocyanide, that is ferricyanide. Ferricyanide, ferrocyanide, ferrous, ferric. Okay, ferric, Fe plus 3, ferrous plus 2. Okay. So you can do as many questions as you can, so that you can boost your confidence. Okay, by simply looking over the complex, you can't get any answer. Just you have to pick your pen and paper and write down all these things. Okay. Next, so what are the drawbacks? What are the drawbacks of Sedgwick's theory? So what are the drawbacks of Sedgwick's theory? First thing. So now here the Lewis concept, the 6, for example, if you are having 6 lone pair of electrons, 6 ligands. So 6 ligands will take 6 lone pair of electrons to the metal atom. 6 lone pair of electrons to metal. That means metal, the charge over the electron density over the metal atom increases. But most probably metal is the most electropositive nature. Metal having most electropositivity character. Okay. But the electron density over the metal atom increases because 6 ligands are donating 6 lone pair of electrons. That means electron density over the metal atom increases because of the relation of 6 lone pair of electrons by ligands. So this will cause conduction to its electropositive nature of metal. That will lowers the stability of the complex. That is first drawback. Okay, electron density of the metal increases, so that is conduction to its electropositivity character. Okay, that's first thing. And the second thing, so few complexes which are not obeying, AKNU, but still they are stable. Okay, there are so many complexes are not obeying AKNU, but they are stable. Okay, these two are the drawbacks of the Sedgwick's theory. And next theory, which is most important theory, valency bond theory. Valency bond theory in 1935 Pauling and Slater. So Pauling and Slater introduced this Bsc-Chemistry-Coordination in 1995 by using concept of hybridization. Okay, so this theory explains a few properties which are not explained by Werner's theory and Zipf's theory, like magnetic properties, magnetic structures of many complexes. Okay, all these things can explained by this Werner's theory. Right? Assumptions. Let's see assumptions one by one. Okay, first assumption was, so metal atom makes available of vacant orbitals, which are equal to its coordination number, So for accepting electron pairs from the ligand forming covalent bond. Okay, so that's first point. So metal atom makes available of vacant orbitals, because in the previous class I told you now. So what is the necessary condition for forming complex compound is metal having vacant d orbitals. There is a B.SC, d orbitals. Okay, so vacant orbitals, and ligand having lone pair of electrons. Now the ligand donating its lone pair of electrons to the central metal atom and forming a coordinate bond. Okay. Now for that purpose, metal having vacant orbitals by accepting electron pairs from the ligand. That is first assumption. Okay. And the second thing, so these vacant orbitals are maybe S, P, D orbitals. So these vacant orbitals, for example, if we are having coordination number is 4. That is 4 ligands we are having. That is 4 ligands donating 4 lone pair of electrons to the central atom. So for accepting those 4 lone pair of electrons from the ligands, metal must have having 4 vacant orbitals. Okay, so those 4 vacant orbitals are maybe S, and P orbitals are 3, Px, Py, Pz. One S orbital, Px, Py, Pz. So total 4 orbitals. So these 4 orbitals are mixed together and forming new orbitals. Those orbitals are called hybrid orbitals, and the process is called hybridization. So what is hybridization? Mixing of atomic orbitals. So for example, we are having 6 ligands. So 6 ligands are donating 6 lone pair of electrons to the central metal atom. That means metal should have 6 vacant orbitals. So there will be 1 s orbital, 3 p orbitals, and 2 d orbitals. Total 6. So these 6 orbitals are mixed together. Initially, these 6 vacant orbitals are mixed together and forming new orbitals. Those are called hybrid orbitals. So the generation how many hybrid orbitals are produced here? Number of vacant orbitals which are equal to number of vacant orbitals are involved in the mixing. Okay, so that is S, P, D orbitals. Those vacant orbitals are S, P, D orbitals are hybrid orbitals. Okay, so that is point number 2. Next, covalent bond. So this covalent bond is formed by the overlapping of vacant orbital of metal, and filled orbitals of ligand, forming covalent bond. So there is quite difference between covalent bond and covalent bond. So in covalent bond, what is covalent bond? Sharing of electron pairs. So here both are having contribution. Both are donating 1 electron and forming one bond, that is one bonding electron. So one bond pair of electron. Okay, one pair of electron. Sharing of electron pairs. What is coordinate bond? In coordinate bond also we are having shared pair of electrons, but those shared pair of electrons are donated by one atom only. That means we are having only one contribution. Okay, one contribution, that is coordinate bond. Okay, but after formation of coordinate bond, this can be considered as covalent bond. Once formed the coordination bond, so that bond will be considered as covalent bond. So that's why it is called covalent bond. Okay, so in this way the covalent bond will be formed. Okay, so the third point is the covalent bond is formed by the overlapping of vacant hybrid orbital of metal and filled orbital of ligand. So that is third assumption. Okay, now so this overlapping, the bond will be strong when this overlapping is strong. Okay, so this overlapping is strong only when these these orbitals are involved in the process called hybridization. Okay, so hybridizers are more directional. That's why they are overlapping more strongly and forming more covalent, strong covalent bond, right? And ligands are classified into two types. That is strong ligands and weak ligands. So strong ligands. So ligands are classified into two types: strong ligands and weak ligands. So what are strong ligands? The tendency to pair electrons. So strong ligands are pairing electrons. So if initially metal having d electrons, initial metal having electrons in d orbitals. So those electrons in d orbitals are paired up because of this strong effect of ligand. Okay, those ligands are called strong ligands. That means electrons are filled against to Husserl. If the complex which contains a strong ligand, the electrons in d orbitals, metal d orbitals, electrons present in d orbitals are filled against to Husserl. What is Husserl? Pairing takes place after all the degenerate orbitals are off-filled. After off-filled, pairing takes place. Against to Husserl means starting from pairing. Okay, right. Next, weak ligands. No such kind of tendency. So which follows Husserl. It is against to Husserl, which follows Husserl. Weak ligands follows Husserl and against to Husserl. So no such kind of tendency here. Here strong ligands have tendency to pair up electrons. Here no pairing. It means it follows as this Husserl. So first filling takes place, next pairing takes place, right? So these are the few assumptions regarding valency bond theory and right. So here inner orbital complex. So what are inner orbital complex? Inner orbital complex, outer orbital complex. Inner orbital complex and outer orbital complex. So inner orbital complex and outer orbital complex. So inner orbital, what are inner orbital complexes? In the hybridization, the name itself indicates inner d orbitals are involved. That means n-1 d orbitals are involved in the hybridization. So those are inner orbital complexes. And nd orbitals are involved. That means outer d orbitals. The name indicates outer. In the hybridization, outer d orbitals are involved. So those complexes are outer orbital complexes. Okay. So what are inner orbital complexes? In the hybridization process, inner d orbitals are involved. For example, if we are having 6 ligands, 6 ligands requires 1 s orbital, 3 d orbitals, and 2 d orbitals. So these 2 d orbitals are inner. These 2 d orbitals are inner d orbitals. So those complexes are inner d orbital complexes. The 2 d orbitals are outer orbital complexes. Outer d orbitals is n d orbitals. That is outer orbital complexes. Okay. Let's take another example. So before discussing example, I will give you one table for you so that you can understand easily. So coordination number, hybridization, example, structure, shape, example. So coordination, if coordination number is 2, hybridization is SP. Coordination number 2, that means 2 ligands are here having. So 1 s orbital, 1 p orbital. Here having 2 orbitals, sp. So these 2 orbitals are mixing together, which gives new orbitals, new hybrid orbitals. How many orbitals are? 1 s orbital, 1 p orbitals are mixing. That means 2 orbitals mixing. That means 2 hybrid orbitals are generated. These 2 sp hybrid orbitals are there. So these 2 sp hybrid orbitals are overlapping with the filled orbitals of ligand. Means shape is linear. Example, Ag NH3 twice. Okay. Second coordination number is 3. sp2 hybridization. Trigonal planar. Hg I3 minus example. Next coordination number is 4. sp3 hybridization. Tetrahedral. Example NiCO4. So if you have coordination number second for DsP2 hybridization square planar NiCN4 2 minus DsP2 hybridization. Coordination number is 5. D2sp3 DsP3 1 plus 1 that is 2 plus 3 that is 5. Okay, so 5 we can talk as DsP3 hybridization. It is trigonal bipyramidal FeCO5. The coordination number is 6, that is D2sp3 octahedral geometry. Octahedral is CONH3 6 times 3 plus. Okay, coordination number is 6, that is D2sp3 hybridization. So here inner d orbital cell involved. So this hybridization itself indicates inner d orbital cell involved. This is inner orbital complex. And if sp3d2, the coordination number is 6, hybridization is sp3d2, that means outer d orbitals. Here, for example, this metal atom belongs to 3D series. For example, this orbital d orbital is 3D and this orbital is 4D. Inner orbital, that is n minus 1, that is 3D. Here it is nd, that is 4D orbitals. So in the hybridization, outer d orbitals are involved. The sp3d2 hybridization, the structure is shaped octahedral geometry COF6 3 minus example. Here NH3 is strong ligand and fluorine is weak ligand. That's why it is forming inner orbital complex and weak field ligand. So that way it is forming outer orbital complexes. Okay. So in the next video, we will be discussing about a few examples regarding all this hybridization like sp3, sp2, sp3. So before that, I will show you a few models for you. Okay, linear. So linear molecule AgNO3 linear. So this is linear molecule and angle is 180 degrees. Okay, 180 degrees. Ag, NH3, NH3. Okay. Next, trigonal planar. So trigonal planar. So ammonia and 2. So this is trigonal planar. So blue color ball is Hg, that is mercury, and 3 iodines forming trigonal planar structure. Okay. Next, tetrahedral. So tetrahedral, one angle is 109 degrees, 28 degrees. Okay, 1 centimeter atom and 4 ligands, right? And square planar. And this is square planar. This one, DsP2 hybridization. And this is trigonal bipyramidal geometry. So 3 atoms in one plane. So above the plane having one atom, below the plane having one atom. Okay, this is trigonal bipyramidal geometry. And last one, octahedral geometry. So this is octahedral geometry. Along x axis 2, along y axis 2, along z axis 2. Overall here are 6 ligands. Okay, right.